Okay, so we have a very important topic that is called elliptic curve cryptography. So people hear it all the time, but do not find introductory explanation to it. This is why every Bitcoin book talks about RSA. But actually in Bitcoin, Ethereum, every digital signature you do, any transaction you do, actually you digitally sign it. When you're transferring Ether or Bitcoin, you actually have to digitally sign your transaction. And that signature actually comes from elliptic curve digital signature algorithm. But since elliptic curves are algebraic objects and hard to explain, all of the Bitcoin books and so on never mentions this, but instead they talk about RSA because they think that public key cryptography consists of RSA, but actually not. So let's try to explain elliptic curve cryptography without going much into detail of algebraic geometry. Okay, let's see how this works. So here's a elliptic curve picture here. Sorry that actually the formula does not appear here, but actually what you here have is that y square equals to x cubed plus ax cubed plus bx plus 1. Sorry for that, you know. I will try to correct it. Sorry, I thought that it fits, but apparently it does not. So depending on your A and B, the picture changes. So let me find the full definition someplace. Yeah, y squared equals to x cubed plus ax plus b. This is a general definition equation of an elliptic curve. Okay, so depending on your choice of A and B, the picture might change like this. So all of them are elliptic curves, but some of them are like independent parts here, like a circular shape and a curve and so on, but sometimes a single piece like this. So it depends on your choice of A and B, but all of them are elliptic curves. So let's see why it is important for cryptography. Points on an elliptic curve generates a group where the points are the elements of the group. Addition of 2 points P and Q is defined as the point as follows. Draw the line that passes through P and Q. It intersects the curve at the third point R. Multiply the y coordinate of R with -1, which means that just take the reflection with respect to x-axis. The resulting point is P plus Q. So recall what we talk about in algebra. We talk about groups. We said that a group consists of a set of elements and an operation. So here the set of elements are points. Operation is defined like this in a very bizarre way, okay? So we also said that a group has to have an identity element. And here we say that there is a point at infinity, which is actually kind of a point at the top of the y coordinate and works like an identity element. And of course, every element has to have an inverse. So let's see how this works, okay? So first, let's look at the addition rule. So assume that I have 2 points P and Q. I define the addition like this. Draw the line that passes through P and Q. We call that only one line can pass through 2 different points, right? So it has to intersect at a third point. This is due to the equation of the elliptic curve. I know that it has to intersect at some point. So instead of looking at it, just take the reflection with respect to x-axis, and now this is P plus Q. So a very strange way of defining an addition operation, but this is how I add 2 points, okay? I'm not adding their coordinates or anything. I'm actually drawing a line and do this. So of course, since we are going to create a group, I need to add the point to itself, right? Because in a group, I can do the group operation on an element itself. So what happens if I add P to itself, right? Here you have 2 different points. Now you are trying to add the P itself. What we do is draw the tangent line here. It has to intersect the curve at the second point. Take the reflection. Now I have 2P. So if you add this point to this point, I will call it 3P. If I draw the tangent from here and add to itself, I will obtain 4P and so on and so forth. So this is the main addition operation. But what is the identity element? So we say that there's a point way up in the infinity through the y coordinates. So here we are dealing with affine coordinates. This is why this definition might seem bizarre. But when you move on to different coordinates, or if you look at this in the complex plane, that point of the infinity actually makes sense, okay? Just trust us that there's a point there at infinity. So why this is the point at infinity? Because we define the inverse of a point as like this with respect with reflection of the x-axis, okay, x coordinates. So if this is a point P, minus P is here, inverse element of P. So why this is the case? At these 2 points means that draw a vertical line which goes to the infinity, right? We say that there's an identity element there. Similarly, if you want to find the inverse of P, again do the vertical line. It passes through the identity element at infinity. It passes here, right? It has to intersect here. And you do the reflection here. So identity element plus P gives the P itself. Agreed? So a very bizarre way of defining a group, but it works. This is really a group. Okay, these are the elements. So let's see how I can use it in cryptography. So a curve like this, if I draw it in R2, sorry, in real L on R, sorry, this is for example, an example of an elliptic curve, y squared equals to x cubed minus 2x plus 1 over R, which means that coordinates are in real numbers, right? But there are infinitely many points on this curve. We call that, when we talk about groups or fields, we always focused on finite groups or finite fields because I'm going to work on real world data. So I need finitely many points, not infinitely many points. So what I do is that I consider it over Z8 and 9, for instance, in this example. So although you have infinitely many points here, the points that has coordinates in Z8 and 9 are this many points, okay? So when you do those additions and identity element, now you will be working on these elements. The good thing is that when you add these 2 points, it gives you another point in the set. So it is really still a group. Okay. So these elliptic curve crypto systems were invented independently by Neil Koblis and Victor Miller in 1985. They really did it independently. They were in 2 different parts of the world at the time. There weren't any internet connection between them and so on. But now both mathematicians realized that such a group might come in handy because we talk about the discrete logarithm problem, and the discrete logarithm problem, the hardness, interactivity depending on the group we worked on, right? This group actually will be harder to solve the discrete logarithm problem. So we focus on elliptic curves over FP, like I did it here, okay? Most standards which specify the elliptic curve cryptographic techniques restrict the order of the underlying finite field to be an odd prime, q equals to p, where this is a huge prime, or a power of 2, like q equals to 2 to the m. So you don't see any standards where you have like 3 to the m or anything. You either work on 2 to the m or very huge prime like p. So let p should be larger than 3, an odd prime. An elliptic curve E over FP is defined by an equation of the form y squared equals to x cubed plus ax plus b, where these coefficients a and b are from FP, our field. Also, it has to satisfy this property, which is 4a cubed plus 27b squared should be different than 0 modulo p. If this is the case, I will call it an elliptic curve, okay, over FP. So this set E of FP consists of all points x, y, where these coordinates are in FP, that satisfy this curve equation. Also, I need to add this special point, which I represented with O as the point at infinity. Okay? So let me show you an example. Let P23, notice that this is a prime number, and consider the elliptic curve y squared equals to x cubed plus x plus 4. So as you can see, I chose A equals to 1 here, B equals to 4 here. So question is this an elliptic curve? Let's calculate this. 4a cubed plus 27b squared modulo 23. It is different than 0. So yes, this is indeed an elliptic curve. So next question is, what are the points on this elliptic curve over F23? You can calculate one by one. For instance, x and y can take values between 0 to 22, right? Let x equals to be 0. You end up with y squared equals to 4. So think about the solutions of this equation. So 2 apparently is a solution. But also 21 square turns out to be 4 in modulo 23. Okay, so you end up with 2 points where x coordinate is 0 and y coordinate is 2 and 21. Right? Now put x equals to 1, you obtain 2 points. Put x equals to 2, it turns out that there's no y in this set that satisfies this equation, so you don't have any points that start with an x coordinate equals to 2. So this way you can try all of them, and you will see that there are 29 points like this. Okay, but of course, if I choose a big prime instead of 23, calculating all of these points one by one will be hard, right? But I need to know how many points I have on the elliptic curve, because that will be my group size. We call that the whole security relies on the size of this. And I want it to be like 256 bits group, okay? Unlike RSA where you need 3000 bits of groups, okay? So how do you count the numbers on an elliptic curve? So in 1985, there is a Scoof paper where he presented a polynomial time algorithm for computing the number of points of an elliptic curve over FQ. The number of points on an elliptic curve over FQ indicates when Q is odd. This means that you have a very large prime, okay? So we know how to count this since 1985. Koblis extended it to the case Q equals to 2 to the m. Scoof's algorithm is rather inefficient in practice because Q is really large nowadays. As I mentioned, I need to have a size of 256-bit group, so Q has to be larger than 2 to the 256. So there are many modifications, many optimizations, but at the end of the day, these algorithms are called Scoof, Elkes, Atkin algorithm received many improvements so that suitable elliptic curves can be generated in a few hours. For more recent publication, you can see such. So randomly choosing an elliptic curve and then counting its points is not that hard. That is what I'm trying to tell you. Okay, so let's look at the group operations. I explained in a geometric sense, but of course, I need to write a code for it, right? I need to mathematical equation so that I can actually do these group operations. So group operations are like this. Adding the point at infinity is the identity element gives you the element back. If you have P as the coordinates x, y, then this addition gives you identity element. So we have minus P as like this. So every point has an inverse like this. Now let's talk about adding P to the Q. Let's say that P has coordinates xy and y1, and Q has the coordinates x2, y2. And here the Q is not equal to P or minus P, okay? So here, this is the point where we draw the tangent line and take the reflection and so on. But this actually turns into the following equations. P plus Q actually gives you the coordinates x3, y3, where you calculate x3 like this and y3 like this. But one thing to notice is that I have a division operation here. But if I work on FP, this division operation actually is a multiplication with the inverse of x2 minus x1. So this is a field operation, not a regular division, because you won't have such a division operation in FP, right? So if you want to add P to itself, you know the P and you want to calculate 2P. Now the coordinate equations are calculated like this. So instead of x2, y2, you don't have that, but you have such an operation here. Okay. So this is the code you need to write when you want to perform these group operations. So let's again look at the example. I choose the same elliptic curve I mentioned before, chose the same field, F23. There's a good thing is that since the number of points on this elliptic curve over F23 is 29, and this is a prime number, this means that this is a cyclic group. Any point other than the identity element is a generator of this group. This means that take a point, for instance, P, and its coordinates is 0 to 0, 2. Add it to itself by using this formula. Okay, you will see that it is this point, 13, 12. Add P to this one. Now you need to use this equation because P and 2P are two different points. you see that it will give you this point. Keep adding p to itself. You will realize that you end up with 0 to 21. This is actually minus p. So you add it to itself and obtain the identity element. So an element can generate all of the other elements in the group. This is called the generator of this group, okay? And this is a cyclic group. Every element does that. Okay, so let me show you an example and see what kind of real-world examples we have. For instance, Bitcoin uses this elliptic curve, sec p 256k1, which is a standardized by Certicom. At that time, it wasn't a NIST standard. Satoshi deliberately chose this, saying that, you know, NSA didn't put a backdoor in because at the time people didn't, have much confidence in NSA involvement in some of the standards. So he deliberately chose this. But nowadays, NIST put this elliptic curve at the appendix of their new standard, saying just to provide interoperability. So elliptic curve is something simple. Y square equals to x cubed plus 7. So A is chosen as 0, B is chosen as 7. And this is defined over Fp, where P is this number. As you can see, it's a huge number, 2 to the 256 minus these small values, but it turned out to be a prime number. So in hexadecimal notation, this P is represented like this, okay? And actually, all points on this curve are valid Bitcoin public keys, okay? So you have a base point G. In hexadecimal notation, it is represented like this. So the first part from here to here, I guess, will be your X coordinate, and the remaining part will be your Y coordinate. So this G actually generates this many elements on this curve. So this will be your actual group order. And actually, any Bitcoin address you generate is a point on this curve, okay? And actually, when you transfer a Bitcoin, what you do is actually sending money to a point on the elliptic curve, okay? So why does this work? Actually, the thing is that what you do is as follows. You choose a private key, a number D, and add G to itself D many times. You end up with a point, and that point is your public key, D is your private key. Okay. So let's see in an example in a minute, but let's correct a few misunderstandings. As I mentioned before, there are many books saying that Bitcoin uses this elliptic curve defined by National Institute of Standards and Technology. This is a quote from a recent book published in 2018 by Wiley. Actually, this is not defined by NIST. Actually, it is deliberately chosen that this is not a NIST curve, okay? Satoshi deliberately did that. So, and there are some quotations from it saying that Satoshi chose this elliptic curve for no particular reason. No, he deliberately chose this, knowing that it is not a NIST standard, okay? Yeah. So as I mentioned before, current NIST drafts and current published versions of digital signature algorithm documents actually put this curve to the appendix so that to provide interoperability.